In the rolling green hills of 19th-century Scotland, long before electricity illuminated the streets or radio waves carried voices across oceans, a young boy wandered through the countryside, sketching patterns of light, water, and movement with childlike wonder. His name was James Clerk Maxwell, a name that would one day become synonymous with the invisible forces shaping the universe, though at the time he was just an inquisitive child who saw beauty where others saw only ordinary things. Born on June 13, 1831, in Edinburgh, Scotland, Maxwell was raised amid both nature's quiet harmony and the mechanical hum of an age just beginning to understand its own potential. His father, John Clerk Maxwell, was an educated man with a passion for invention, while his mother, Frances Kay, instilled in him a love for learning and faith in the pursuit of truth. From these two influences, his father's curiosity and his mother's nurturing intellect, emerged a mind that would one day decode the hidden rhythms of light and electricity. Even as a child, James seemed fascinated by the unseen. He would stare for hours at the reflections in puddles, tracing the shapes of ripples and asking why light bent or water shimmered. At just 8 years old, he began experimenting with homemade gadgets, using strings, mirrors, and bits of glass to study how light behaved. His early notebooks, preserved today, reveal not just a precocious intellect, but a poetic sensitivity toward the laws of nature. His sketches were detailed yet expressive, his notes filled with wonder rather than arrogance. He seemed to sense that every movement, every flicker, every reflection was part of a grander design, a harmony waiting to be understood. But his childhood was not without hardship. When James was 8, his mother passed away from abdominal cancer. Her death was a devastating loss, one that could have broken his spirit, but instead it deepened his introspection. Deprived of maternal guidance, he turned to nature and study for solace. His father, determined to honor his wife's memory, took charge of his education. Together, they built simple mechanical contraptions, observed the motion of pendulums, and studied geometry by candlelight. For young James, learning was never confined to books. It was an adventure that merged curiosity and creativity. At the age of 10, he entered the Edinburgh Academy, a school that emphasized classical education but often failed to nurture unconventional minds. The other students mocked him for his slow speech and country accent, calling him dafty. But while they teased, he listened, observed, and imagined. During those years, his interest in geometry blossomed. He would spend hours constructing complex shapes with bits of string and drawing intricate diagrams of ovals and circles, asking why certain patterns repeated in nature. His teachers noticed his extraordinary talent for mathematics, but even they couldn't predict how far it would take him. At just 14, he wrote his first scientific paper on the description of oval curves, a work so advanced that it was presented to the Royal Society of Edinburgh by his professor, not him, because he was too young to attend. There was something extraordinary about the way Maxwell thought. He didn't just calculate, he visualized. Where others saw equations as abstract symbols, Maxwell saw them as windows into nature's secret order. He imagined electric and magnetic fields as invisible threads weaving through space, connecting everything in a vast web of energy. Even as a teenager, his way of thinking was years ahead of his time, rooted in both imagination and logic. His curiosity wasn't just intellectual, it was spiritual. He believed that to understand nature was to glimpse the mind of creation itself. When Maxwell entered the University of Edinburgh, at 16, he immersed himself in every field that caught his interest: mathematics, physics, philosophy, and even poetry. He studied under some of the greatest minds in Scotland, yet he often pursued his own experiments outside the curriculum. He built models of spinning tops to understand rotation, studied the elasticity of materials, and played with polarized light to explore how color and vibration interacted. His notebooks from this period are filled with sketches that look almost like art, mathematical beauty expressed through form and pattern. It was as though he could feel the pulse of the universe beneath the equations. In 1850, Maxwell moved to the University of Cambridge, entering the world's most prestigious intellectual arena. There, he encountered fierce competition, but also the inspiration that comes from being surrounded by brilliance. Cambridge was alive with the spirit of scientific discovery, yet many of its scholars were still rooted in Newtonian mechanics, the idea that the universe was like a great machine governed by precise but separate laws. Maxwell, however, sensed that these separate forces, electricity, magnetism, light, were not isolated parts but expressions of one deeper unity. It was a conviction that would guide him for the rest of his life. But the journey to that realization began with something simpler: curiosity. He would walk through the halls of Trinity College late at night, holding a small candle, reading old papers by Newton, Faraday, and others who had tried to grasp the nature of light. To Maxwell, these weren't just historical studies, they were conversations across time. He felt as if he was continuing a dialogue begun centuries before, adding his voice to the eternal question of how the universe truly worked. Outside of academia, Maxwell was known for his warmth and humor. He played the guitar, recited poetry, and wrote witty verses to entertain friends. Unlike many scientists of his era, he didn't view science as cold or mechanical. It was alive, musical, and filled with wonder. His faith, too, played a quiet but steady role in his worldview. He once wrote that the goal of science was to think God's thoughts after him, not in arrogance, but in reverence. For Maxwell, discovery was a form of worship, a way of understanding the divine symmetry in all things. Despite his brilliance, Maxwell never lost his humility. He often doubted his own worth, fearing that he might never contribute something truly lasting. Yet even in moments of uncertainty, he kept experimenting, kept questioning, kept connecting dots that others overlooked. When he wasn't conducting physical experiments, he was conducting thought experiments, imagining, for instance, what it would mean if light behaved as both a particle and a wave. These quiet mental explorations would later become central to the revolution of modern physics. During his university years, Maxwell also became fascinated with color and perception. He designed one of the world's first color photographs by projecting red, green, and blue filters onto a screen, an experiment that would later influence how cameras, screens, and displays work today. His curiosity had no boundaries. He saw science not as isolated disciplines, but as one interconnected masterpiece. The young man from Scotland had grown into a visionary thinker, yet his manner remained gentle and unassuming. Friends and professors noticed how deeply he could immerse himself in both thought and feeling. When others spoke of formulas, Maxwell spoke of patterns, symmetry, and the poetry of the universe. His mind worked like a bridge between reason and imagination, between calculation and creation. Every observation was a clue, every problem a mystery worth solving. He would look at a simple magnetic needle twitching on a table and imagine entire fields of force flowing invisibly through space. He had not yet written the equations that would define his name, but already the seeds of his great unification were forming in his mind. The social environment around him, however, was not always supportive. The scientific world in the mid-19th century was dominated by empiricism. Only what could be directly observed was accepted as real. Maxwell's ideas about invisible fields and waves seemed too abstract, even mystical. Yet that didn't stop him. He had faith not only in mathematics, but in imagination itself. He believed that even if we couldn't see something, the harmony of equations could reveal its truth. This belief, that the unseen can be known through logic and beauty, became the defining principle of his life's work. As he matured, Maxwell's worldview continued to expand. He saw patterns in everything: the vibrations of light, the oscillations of sound, the ripples of water. He once remarked that nature is a grand symphony, and physics is the art of discovering its rhythm. This poetic sense of unity allowed him to see connections that others missed. To him, electricity wasn't merely a spark, it was part of a grand wave that traveled through the fabric of space. Light wasn't just illumination, it was a messenger of motion and energy, carrying information across the cosmos. These were radical ideas for a world still rooted in visible mechanisms. Even in his early experiments, Maxwell's curiosity reflected a rare blend of creativity and precision. He could spend hours fine-tuning a simple mechanical model just to observe how it behaved under different conditions. To outsiders, it looked obsessive, but to him, it was a meditation. Each experiment was a dialogue between mind and nature, between question and answer. He often worked alone in silence, guided not by ambition but by a deep love for understanding. His writings from this time show not the pride of a genius, but the humility of a seeker. He once wrote, "I have never made a discovery, only found what was waiting to be seen." In those early years, he also began to sense that his work could bridge not just scientific gaps, but philosophical ones. He was fascinated by how abstract mathematics could describe real, tangible forces. He saw in this a profound truth, that nature's laws were written in a language both logical and beautiful, and it was the duty of science to translate it. This conviction gave him strength even when others doubted his unconventional ideas. By his mid-20s, Maxwell's intellect was already recognized across Britain. He had published several papers that combined deep mathematical insight with physical understanding. Yet, despite his growing reputation, he remained the same gentle, curious soul who once played with light and mirrors in the Scottish hills. Fame never interested him. What mattered was the pursuit of truth, the elegance of a solution, the thrill of uncovering a mystery that had long been hidden. The essence of Maxwell's early life can be summed up not in achievements but in his relentless curiosity. He was driven by a sense of wonder so deep that it transcended ambition. He wanted to know why light glowed, why magnets pulled, why colors shimmered in patterns, why nature seemed to follow certain laws with mathematical grace. It was this questioning spirit that would lead him, years later, to the great discovery that light itself was an electromagnetic wave, a revelation that would open the door to the modern world. The story of young James Clerk Maxwell is not just the story of a prodigy, it is the story of what happens when imagination and intellect walk hand in hand. His early life was a crucible of curiosity, shaped by love, loss, faith, and fascination. The boy who once marveled at ripples in a pond would one day explain the ripples of energy that travel through space itself. Every spark of his childhood curiosity became a spark of understanding that illuminated the path of science for generations to come. He was a dreamer who refused to separate emotion from reason, a scientist who saw the poetry in numbers, and a thinker who dared to look beyond the visible into the invisible fabric of existence. In the quiet Scottish fields where his journey began, a child once asked the world its simplest and deepest question: why does it work the way it does? The universe, patient and vast, would one day answer him through his own equations. As Maxwell grew from the curious young scholar of Edinburgh into a mature mind at Cambridge and beyond, the seeds of his early wonder began to bloom into profound insights that would soon reshape physics forever. Yet his journey remained one of quiet reflection rather than public acclaim. He was not driven by fame, but by the deep inner necessity to understand the invisible harmonies that held the cosmos together. The same child who once watched ripples in a pond now saw the universe itself as a vast ocean of energy, vibrating with laws waiting to be discovered. When he began teaching and researching, Maxwell brought with him a philosophy that learning was not the accumulation of facts, but the cultivation of vision. He often told his students that to study nature was to listen for a melody so faint that only patience could reveal it. His lectures were filled with analogies, poetry, and wit. He would compare equations to musical chords and describe light as the song of the electromagnetic field. The students sometimes struggled with his abstract style, yet they sensed they were in the presence of a mind seeing further than most could imagine. In his quiet moments, Maxwell would walk through the countryside or sit beside his instruments, sketching ideas that blurred the line between art and science. He was fascinated by how simple shapes, circles, spirals, ellipses, could describe motions of planets, oscillations of sound, or the vibration of light. Each curve to him was a whisper from nature. He once wrote that the purpose of science was not merely to predict, but to understand, not merely to measure, but to perceive beauty. This aesthetic sense guided his mathematics. He believed that a correct theory must also be elegant, because nature herself was built upon elegant simplicity. As his research deepened, Maxwell's intellectual curiosity extended far beyond physics. He studied philosophy, theology, and even psychology, exploring how humans perceive colors and forms. His experiments on color vision were revolutionary, he discovered that all hues seen by the human eye could be produced by mixing just three primary colors: red, green, and blue. From this insight, he created the first color photograph, an image of a tartan ribbon, projected through three colored filters. Though the process was primitive, the principle was profound. In that shimmering ribbon lay the foundation of modern color imaging, from television screens to digital displays. To Maxwell, it was another example of unity, the same unity that guided his thinking in physics, multiple elements combining to produce one continuous harmony. Despite his deep insights, Maxwell's personal life remained remarkably humble. In 1858, he married Catherine Dewar, a woman who shared his love for quiet study and faith. Their marriage was a partnership of minds and hearts. She assisted him in experiments, read his drafts, and managed the household with warmth and intelligence. They lived simply, often in rural settings where he could think and write in peace. Visitors described Maxwell as cheerful, humorous, and deeply kind, a man who could discuss complex theories one moment and recite a funny verse the next. His laughter was genuine, his humility disarming. He seemed unaware that he was already walking the path toward becoming one of the greatest scientific minds in history. In these years of domestic tranquility, Maxwell continued to explore the mysteries that had fascinated him since childhood. He became particularly intrigued by the invisible interplay between electricity and magnetism. Scientists before him, such as Michael Faraday, had discovered that a changing magnetic field could produce an electric current, and vice versa. But the mechanism behind this remained a mystery. What was the nature of this force? How did it travel through space? What invisible medium carried it from one point to another? Maxwell, drawing from his early habit of visualizing rather than merely calculating, began to imagine space itself as filled with lines of force, elastic, vibrating threads connecting all points. To most of his contemporaries, this idea was almost mystical. They preferred to think of forces as simple actions between particles. But Maxwell believed that reality was more subtle and more beautiful. The universe, he thought, was not empty but alive with motion, every region of space trembling with the potential of energy. He began to express these ideas mathematically, weaving together electricity and magnetism into a single coherent framework. Each equation he wrote was like a note in a grand symphony, and together they began to sing of something astonishing: the existence of electromagnetic waves, traveling at a constant speed, the speed of light. This realization was the culmination of the curiosity that had guided him since boyhood. When he compared the numerical value of the speed predicted by his equations to the known speed of light, the match was so precise that it seemed almost miraculous. In that moment, Maxwell understood that light itself was an electromagnetic phenomenon. The glow of a candle, the shimmer of a rainbow, the spark of lightning, all were manifestations of vibrating electric and magnetic fields moving together through space. The unity he had always sensed in nature was now revealed in mathematical perfection. Though this revelation came later in his life, its roots lay in the young boy who once played with mirrors and asked why light behaved as it did. His early curiosity had matured into a theory that would revolutionize science. Yet, even at the height of his achievement, Maxwell remained modest. When asked about his discovery, he said he merely followed where the mathematics led. He never claimed greatness, never sought titles. His reward was understanding, the deep satisfaction of seeing how the universe fit together like a perfectly balanced equation. Maxwell's work soon began to influence every corner of science, but he did not live to see its full impact. In his final years, his health began to decline. Even as illness weakened his body, his mind remained clear and active. He continued teaching, corresponding with colleagues, and refining his theories. His wife cared for him devotedly, reading to him from poetry and scripture as he rested. When asked about his approaching death, Maxwell spoke calmly, saying that he had faith in both the physical and the spiritual laws of creation. He passed away in 1879, at the age of 48, the same age at which his mother had died decades earlier. In the years that followed, the world slowly began to realize the magnitude of his contributions. His equations became the cornerstone of modern physics, inspiring generations of scientists, including Einstein, Planck, and Hertz. But behind the equations was the spirit of the young boy who had once stared at a beam of light and wondered why it danced. That childlike wonder never left him. It merely deepened into wisdom. Maxwell's early life and intellectual curiosity remain a testament to the power of imagination in science. He did not approach the world with arrogance, but with awe. He believed that discovery begins not with certainty, but with wonder, the willingness to ask, to doubt, to explore. His mind was a bridge between the tangible and the invisible, between art and mathematics, between the physical and the spiritual. Even today, every radio transmission, every beam of light, every Wi-Fi signal carries within it the legacy of Maxwell's youthful curiosity. His life reminds us that great discoveries do not emerge from ambition alone, but from patience, humility, and the courage to follow questions wherever they lead. He once wrote that the study of nature should make us rejoice in the greatness of the works of the Lord, a reflection of his belief that science was not in opposition to faith, but a celebration of creation itself. In a world that often values speed over depth, Maxwell's example stands as a quiet rebuke. He listened more than he spoke, observed more than he concluded. He taught that true understanding comes from stillness, the kind of stillness in which one can hear the hum of the universe. His genius lay not only in his equations but in his way of seeing, his capacity to perceive unity where others saw division. If we look back upon his early years with this in mind, we can see how every small event, the loss of his mother, the teasing at school, the endless experiments with light and color, shaped the character that would later unify the forces of nature. Each challenge honed his empathy, each question sharpened his intellect. The young Maxwell did not know that he would one day transform physics, but he pursued knowledge with such purity of intent that greatness followed naturally. His life also reminds us that genius is not born from isolation, but from curiosity nurtured by love. The gentle encouragement of his parents, the companionship of his wife, the inspiration of his teachers, all played their part in the symphony of his growth. He carried their influence like a melody throughout his life, blending it with his own insights until the music of understanding was complete. As we reflect on Maxwell's journey from the hills of Scotland to the heights of theoretical physics, we realize that his story is not only about science, it is about vision. He saw the universe not as a collection of separate phenomena, but as a single, coherent whole, bound together by invisible laws of harmony. This holistic vision, born of childhood wonder, became the foundation of modern physics and continues to echo through every technological marvel of our age. And so, when we look at the glowing screens that illuminate our nights or listen to voices carried invisibly through the air, we are, in a sense, listening to the echoes of Maxwell's childhood curiosity. Each flicker of light, each signal sent through space, is a tribute to the boy who refused to stop asking why. His life teaches that curiosity, when guided by humility and imagination, can unveil the very architecture of the universe. In the end, James Clerk Maxwell's early life was not merely a prelude to his discoveries, it was the foundation upon which they were built. The same imagination that saw beauty in geometry, the same patience that studied ripples in water, the same courage that endured misunderstanding, all combined to create a mind capable of revealing the electromagnetic nature of light itself. His story is the story of a soul who saw unity where others saw fragments, who heard music where others heard silence, and who, through his quiet genius, made it possible for humanity to understand the radiant energy that connects every corner of existence. Even now, more than a century after his passing, Maxwell's presence lingers wherever light moves and electricity flows. His legacy lives not only in the equations that bear his name, but in the enduring truth that wonder is the seed of knowledge. The young Scottish boy who once chased the glimmer of sunlight across a puddle gave the world a new vision, a way to see the unseen, to understand the unspoken, to feel the pulse of the cosmos. His early curiosity, nurtured by love and guided by imagination, became the spark that illuminated modern science. And in that spark, the forgotten genius found immortality, forever lighting the path for all who dare to ask the question that began his journey: why does the world shine the way it does? In the quiet rooms of 19th century Cambridge, where chalk dust mingled with the faint scent of oil lamps, a young James Clerk Maxwell sat before a blackboard covered in curves, loops, and equations that seemed almost alive. Each line he drew was not merely mathematics. It was an attempt to sketch the heartbeat of the universe. Electricity and magnetism, two forces known yet poorly understood, had long stood apart in the minds of scientists. For centuries they had been treated as separate mysteries, cousins in nature but strangers in theory. But Maxwell looked upon them with different eyes. To him, they were not opposites but harmonies in the same grand symphony, two manifestations of a single hidden force that moved through everything like music through the air. Long before Maxwell began his great work, others had already glimpsed fragments of the truth. In the early 1800s, scientists such as Hans Christian Ørsted and André-Marie Ampère discovered that electric currents could generate magnetic fields. Later, Michael Faraday, Maxwell's great inspiration, showed that changing magnetic fields could in turn induce electric currents. It was a breathtaking discovery, revealing that electricity and magnetism could give birth to each other. Yet despite these breakthroughs, the underlying unity remained elusive. The world knew what happened, but not why. Faraday, though brilliant, lacked the mathematical tools to express his ideas with precision. His notebooks were filled with sketches of invisible lines of force that curved and twisted through space, carrying energy from one place to another. Many of his contemporaries dismissed these lines as mere imagination, but Maxwell saw something different in them, something profound. He believed that Faraday's intuitive drawings were not metaphors but physical realities. He began to translate those lines into the language of mathematics, giving them a structure that could be measured, tested, and understood. It was a bold move, one that few of his peers fully appreciated at the time. While others spoke of invisible fluids and mechanical forces, Maxwell spoke of fields, continuous, dynamic entities that filled all of space. He imagined the electric and magnetic forces not as separate threads, but as intertwined vibrations in a vast cosmic fabric. It was as though he could feel the pulse of energy flowing through the universe, and his equations were the rhythm by which he sought to describe it. In the 1850s, Maxwell began formulating the theories that would change everything. He studied Faraday's experiments obsessively, searching for patterns that could be expressed mathematically. He asked himself how the lines of magnetic force might move, how electric charges might respond, how energy might propagate through the ether, the hypothetical medium thought to carry light and force through empty space. Every detail fascinated him. He imagined small mechanical models in his mind, tiny rotating vortices in the ether, wheels and gears spinning invisibly, transferring motion and energy. These were not literal machines, but analogies, tools of thought to visualize what could not be seen. To Maxwell, the unseen was not unknowable. It simply required imagination guided by mathematics. The challenge before him was enormous. Electricity and magnetism were governed by many separate laws, discovered piecemeal over decades. Coulomb's law for electric forces, Ampere's law for magnetic fields, Faraday's law of induction, Gauss's law for electric charges. Each worked well in isolation, yet they lacked a unifying principle. Maxwell's genius lay in his ability to see connections where others saw divisions. He realized that if these laws were to coexist consistently, something new was needed, an additional term that would link electric and magnetic effects in motion. He spent months exploring the mathematical consequences, often filling pages with dense equations only to cross them out and start again. Yet beneath the calculations, there was a vision forming, a sense of something whole and beautiful waiting to be revealed. In 1861, that vision began to crystallize. Maxwell proposed that a changing electric field could create a magnetic field, just as Faraday had shown that a changing magnetic field could induce electricity. This simple but revolutionary symmetry completed the circle. It implied that electricity and magnetism were not two forces acting upon each other, but two expressions of the same field, each capable of generating the other. From this realization emerged a new picture of nature: electromagnetic waves, self-sustaining oscillations of electric and magnetic fields that travel together through space. And when Maxwell calculated the speed of these waves using known constants for electric and magnetic effects, he found something astonishing. It was equal to the measured speed of light. The result sent a thrill through him. Light, that ancient mystery of philosophers and physicists alike, was not separate from electricity and magnetism. It was electricity and magnetism, waves of the electromagnetic field vibrating through space. For the first time in human history, light had been understood not as a metaphysical phenomenon, but as a natural consequence of unified physical laws. In that instant, Maxwell bridged the gap between optics and electromagnetism, between what could be seen and what could only be felt. It was one of the most profound moments in science, comparable only to Newton's discovery of gravity or Einstein's later revelation of relativity. But this unity did not come easily, nor was it immediately celebrated. Many scientists of the time found Maxwell's approach too abstract. They preferred direct observation and experiment, while Maxwell's theories lived in the realm of mathematics and imagination. Even Michael Faraday himself, the man whose work had inspired it all, struggled to grasp the full implications of Maxwell's equations. Yet Maxwell remained patient. He was not seeking recognition, he was seeking truth. He continued refining his ideas, writing paper after paper to explain how electric and magnetic energy flowed through space, how fields could store and transmit power, how light and radio waves were simply different manifestations of the same underlying reality. To him, every calculation was an act of discovery, every formula a window into the invisible. He once described the satisfaction of his work as similar to hearing a faint melody growing clearer with each note. He could sense the harmony in the laws of nature, a harmony that no one else had yet heard. Even when he doubted himself, he trusted the music of his equations, and in that faith, he found the courage to keep exploring. Maxwell's field theory was not only a scientific revolution, but a philosophical one. It changed the way humanity thought about space itself. Before him, space was seen as an empty void, a stage upon which forces acted at a distance. After him, space became something alive, filled with continuous fields of energy that could ripple, twist, and vibrate. His work transformed the static world of Newtonian mechanics into a dynamic, interconnected universe. It was a conceptual leap so vast that it would take decades for others to fully appreciate it. He imagined invisible waves stretching across the cosmos, their electric and magnetic components intertwined like dancers in perfect step, one leading, the other following, exchanging energy as they moved. He wrote of this relationship with quiet awe, describing how we can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. These words were more than scientific speculation. They were poetry in motion, the articulation of a vision that blended reason and wonder into one. Though Maxwell worked in an age without the technological tools to verify his theories, he trusted the logic of his mathematics. He could not see electromagnetic waves, but he knew they must exist. Years later, Heinrich Hertz would confirm their reality through experiment, demonstrating that Maxwell's predictions were true, that invisible waves could indeed travel through space, carrying energy at the speed of light. This validation came after Maxwell's death, yet it cemented his place as the founder of modern electromagnetism. Even in the midst of this intellectual triumph, Maxwell remained remarkably human. He was known to laugh heartily, to sing hymns, and to compose verses that mixed humor with insight. His colleagues marveled at how such a profound thinker could remain so gentle, so modest. He often compared the beauty of equations to the beauty of nature, saying that both reflected an underlying order too perfect to be accidental. His faith was not in conflict with his science, it was its foundation. For him, the unity of electricity and magnetism was not merely a technical achievement, it was a glimpse into the divine coherence of creation. As he refined his equations, he began to realize that they could be written elegantly in a compact form, a system of just four relationships that expressed the entire behavior of electric and magnetic fields. These would later be known simply as Maxwell's equations, though at the time even he did not realize how monumental they would become. They described how electric charges create fields, how magnetic poles interact, how fields induce one another, and how electromagnetic waves propagate through the void. From these four lines of mathematics flowed the entire electromagnetic theory, one of the most beautiful and powerful frameworks ever conceived. To the modern world, these equations are as fundamental as DNA is to life. They explain everything from the light of stars to the signals that carry our voices across continents. But in Maxwell's time, they were almost incomprehensible in their depth. Many dismissed them as elegant curiosities with little practical use. Maxwell, however, knew that the future would prove otherwise. His imagination had already traveled far beyond the instruments of his day. He envisioned waves that could carry messages through air, invisible connections spanning distances once thought impossible. He could not build the radio, but his equations whispered that such a thing was possible. Even as the scientific establishment hesitated to embrace his ideas, Maxwell continued his work undeterred. He was not a man of confrontation, but of quiet perseverance. His letters reveal a mind constantly turning over questions, refining theories, and seeking ever more elegant expressions of truth. He believed that the beauty of a theory was evidence of its correctness, that the laws of nature, if truly understood, would reveal symmetry and grace. And so he labored not merely as a physicist, but as a kind of artist, shaping the invisible into form through the medium of mathematics. By the end of his life, Maxwell had done what no one before him had achieved. He had united electricity, magnetism, and light into a single theoretical framework. The forces that once seemed separate now danced together in perfect balance. The boy who had once watched the shimmer of water and the play of light had found their secret kinship in equations that would outlive him by centuries. And though his health began to fail, he never stopped marveling at the wonder of it all. In his final writings, he reflected on how far science had come, from sparks and compasses to a vision of the universe filled with waves of energy. Yet he knew that the journey was not over. His work was a beginning, not an end, a foundation upon which others would build. Indeed, it was upon Maxwell's unification that Albert Einstein would later construct the theory of relativity, declaring that the special theory of relativity owes its origins to Maxwell's equations. But in those early days, long before fame or recognition, Maxwell's laboratory remained a sanctuary of curiosity. Each spark, each flicker, each mathematical curve was a conversation with the universe, and in those silent exchanges between mind and mystery, he uncovered one of the greatest truths ever known, that electricity and magnetism are but two faces of the same universal force, bound together by the elegance of nature's design. Even as Maxwell's mathematical vision of electricity and magnetism took form, he remained acutely aware of the broader implications of his work. He understood that what he had discovered was not merely a set of abstract equations, but a language describing the hidden rhythms of the universe. Each term in his equations was like a note in a symphony, each relationship a chord resonating with the harmony of nature. In quiet contemplation, he would trace the lines of force across imaginary space, feeling the subtle interplay of electric and magnetic energy, imagining waves propagating invisibly, effortlessly, carrying the secrets of light itself. For Maxwell, the universe was not mechanical and cold, it was vibrant and alive, a grand theater of motion and interaction. He devoted countless hours to considering how these fields could move and interact. His thought experiments, which often took the form of imagined vortices and elastic media, were far ahead of their time. He pictured electric lines of force stretching through space like taut strings, transmitting energy with precision and regularity. Magnetic lines would circle these electric forces, responding instantaneously, weaving together a seamless fabric of motion. To anyone who observed him at work, it must have seemed almost mystical. Yet behind every visualization lay rigorous mathematics, carefully tested against known laws and empirical observations. Maxwell's genius lay in marrying imagination with exact reasoning, intuition with proof. His contemporaries often struggled to grasp this new paradigm. Many scientists of the mid-19th century were accustomed to action at a distance concepts, where forces seemed to leap instantly across empty space. Maxwell, however, rejected the notion of instantaneous action. He insisted that all electromagnetic effects propagate through space in a continuous and measurable way. This was a profound conceptual shift. It transformed the way physicists thought about causality and the transmission of energy. In essence, Maxwell was teaching the world to think in waves rather than points, in fields rather than isolated particles. In 1865, Maxwell published his seminal paper, A Dynamical Theory of the Electromagnetic Field, in which he fully articulated the interconnectedness of electricity, magnetism, and light. This work was revolutionary in scope and elegance. It introduced the concept that changing electric fields could generate magnetic fields, completing the symmetry that Faraday had glimpsed but could not quantify. It described how electromagnetic disturbances travel through space at a speed determined entirely by fundamental constants, effectively revealing the physical nature of light itself. Maxwell had unified what had once seemed disparate phenomena into a single theoretical framework, providing a clear map of the invisible currents that govern the universe. Yet the impact of this work was not immediately recognized. Many contemporaries found his ideas abstract and counterintuitive. The notion that invisible waves could fill space, carrying energy without any apparent medium, challenged long-held intuitions. Even some of his closest colleagues struggled to grasp the full significance. Faraday, his lifelong inspiration, continued to think in terms of lines of force rather than precise mathematical formalism. But Maxwell persisted, confident that the beauty of his equations reflected the truth of nature. He once remarked that if the universe's laws were indeed harmonious, then the mathematics describing them must themselves be elegant. Maxwell's revolutionary approach went beyond mere unification. It opened the door to entirely new ways of thinking about physical phenomena. By treating electric and magnetic effects as inseparable components of a dynamic field, he laid the groundwork for understanding energy not as a static quantity, but as something that could propagate, interact, and transform. This concept would later become central to nearly every branch of modern physics, from optics and electromagnetism to quantum mechanics and relativity. Maxwell had provided a conceptual lens through which the invisible could be seen, the intangible could be measured, and the abstract could be made real. In his personal notes, Maxwell often reflected on the philosophical significance of his work. He wrote about the unity of nature, the interdependence of forces, and the harmony inherent in physical laws. To him, understanding electromagnetism was not just a scientific pursuit, but a form of aesthetic and spiritual insight. The universe, he believed, was ordered in such a way that even the most complex phenomena could be expressed through simple and elegant relationships. This conviction gave him the patience to labor over equations, refine proofs, and explore every possible consequence of his theories. It also allowed him to view failure not as defeat, but as a step toward deeper understanding. While Maxwell's equations were a triumph of theoretical physics, they also had profound practical implications. By describing how electromagnetic waves propagate, they foreshadowed technologies that would reshape human civilization. Long before radio, television, or wireless communication existed, Maxwell's work implied that energy could be transmitted invisibly across distances. He imagined waves moving through space, unseen yet powerful, carrying light, heat, and perhaps even signals. Though he did not live to build these technologies himself, his vision set the stage for others to do so. Heinrich Hertz's experiments in the late 1880s would finally demonstrate the existence of radio waves, confirming Maxwell's predictions and ushering in a new era of human connectivity. Maxwell's revolutionary work also changed the way scientists approached theory itself. He demonstrated that imagination and mathematics could be as important as experimentation in discovering truth. While experiments grounded theory in reality, Maxwell showed that rigorous thought experiments and logical reasoning could reveal phenomena beyond the reach of contemporary instruments. His approach combined empirical evidence with conceptual daring, providing a model for future physicists such as Albert Einstein, who would later describe Maxwell's equations as the foundation of the special theory of relativity. In this way, Maxwell's curiosity-driven work not only solved existing mysteries but also illuminated paths to discoveries that had yet to be imagined. Despite the groundbreaking nature of his discoveries, Maxwell remained remarkably humble and accessible. He continued to teach, write, and correspond with colleagues, blending rigorous analysis with playful insight. His personality, gentle, humorous, and deeply empathetic, allowed him to communicate complex ideas in a way that inspired others. He often used vivid metaphors, comparing lines of force to streams of water or magnetic fields to invisible ribbons moving through space. This combination of precision and imagination made his work not only understandable but compelling, and it revealed the mind of a scientist who saw beauty in truth. Throughout his career, Maxwell continued to explore the implications of the electromagnetic field. He considered how energy could be stored, transferred, and radiated. He investigated the behavior of dielectrics and conductors, the interactions of charges in motion, and the subtle nuances of light polarization. Each study, no matter how specialized, contributed to a unified picture of nature's invisible scaffolding. His work was holistic. He did not see separate problems but facets of a single cosmic structure. It was this holistic perspective that distinguished him from other physicists of his time and allowed him to make connections that others could not see. Maxwell's revolutionary work also carried philosophical weight. He challenged the idea that forces acted at a distance without mediation. Instead, he proposed that space itself was an active participant in physical processes, filled with continuous fields that could ripple and interact. This was a radical shift in thinking, anticipating later developments in field theory, relativity, and even quantum mechanics. By reconceptualizing the universe as a network of interacting fields, Maxwell changed the very lens through which science interprets reality. It was a vision that combined rigor, imagination, and intuition, demonstrating that mathematics could reveal truths about the unseen as reliably as instruments reveal truths about the seen. Even as the scientific world slowly began to grasp the implications of his work, Maxwell's health began to decline. The same mind that had tirelessly explored invisible currents and field lines now struggled with illness, yet he continued his research and teaching with unwavering dedication. He corresponded with students, revised papers, and refined equations, never losing sight of the vision that had guided him since his youth. He remained committed not to recognition or acclaim, but to the pursuit of understanding, a pursuit that had been his guiding principle since the boyhood days of studying ripples in a pond and reflections in a window pane. The full significance of Maxwell's unification of electricity and magnetism would only be realized after his death, yet the seeds of its impact were already evident. His field theory explained light, radio waves, and electrical phenomena. It predicted behaviors that had never been observed. It challenged assumptions about the nature of space, energy, and causality. Maxwell had not merely solved a problem, he had revealed a deeper order in the universe, an order that subsequent generations of physicists would build upon to uncover quantum mechanics, special and general relativity, and the entire technological world we inhabit today. In reflecting on Maxwell's revolutionary work, one sees the culmination of a lifetime of curiosity, imagination, and meticulous reasoning. The boy who once watched light dance across puddles had grown into a man who revealed the dance of electromagnetic energy throughout the cosmos. His genius lay not only in discovering the unification of forces but in doing so with an elegance and clarity that continues to inspire. The equations he left behind are more than symbols. They are a testament to the power of thought, vision, and persistence, and a reminder that the universe can be understood through the careful blending of observation, imagination, and logic. Maxwell's legacy is all around us. Every wireless signal, every light bulb, every device transmitting information invisibly across space is a product of his insight. Yet beyond the practical applications, his work carries a deeper lesson, that the universe is coherent, that invisible forces connect everything, and that through careful reasoning and boundless curiosity, humans can glimpse the hidden architecture of reality. Maxwell's revolution was not simply scientific, it was philosophical, aesthetic, and profoundly human. Even now, more than a century later, physicists continue to build upon his foundation. From the design of antennas and radar systems to the understanding of particle physics and cosmology, Maxwell's equations remain central. They are proof that curiosity, disciplined thought, and a willingness to imagine the invisible can transform the way we understand our world. Every flicker of electromagnetic energy that passes through the universe echoes his vision, his insight, and his quiet, persistent genius. Maxwell's work connecting electricity and magnetism was a triumph of intellect and imagination. It was a journey from observation to theory, from abstract visualization to predictive mathematics. It reshaped our understanding of light, energy, and the very nature of space itself. And it serves as a reminder that revolutionary ideas often begin with curiosity, the desire to ask questions, to see connections, and to follow the thread of insight wherever it may lead. Maxwell's discovery of the unity of electricity and magnetism transformed science, inspired future generations, and ultimately made possible the technological world we live in today. In contemplating Maxwell's achievement, one realizes that true genius is rarely about power or recognition. It is about the capacity to perceive connections invisible to others, to follow imagination with rigorous reasoning, and to persist in pursuit of understanding even when the world does not yet see the vision. Maxwell's work connecting electricity and magnetism embodies all these qualities. It is a story of wonder, insight, and determination, a story that reminds us that the invisible can be revealed, the abstract can be understood, and the universe itself can be glimpsed through the eyes of one extraordinary mind. In the quiet study of his Cambridge room, James Clerk Maxwell contemplated a problem that had haunted physicists for decades: the apparent disconnection between the forces of nature that shaped our world. Electricity moved with a strange independence, magnetism followed patterns no one fully understood, and light traveled in ways that seemed mysterious, untethered, and yet consistent. Many had attempted to describe these phenomena separately: laws for electric charges, laws for magnetic poles, rules for light, but no one had captured the underlying unity. Maxwell, with his extraordinary vision, realized that these separate threads could be woven together into a single tapestry, a harmonious framework that could explain not only what was seen, but also what was invisible, what was felt but could not be touched. He imagined the universe as a network of interacting fields, like a vast symphony in which each force was a distinct instrument, yet inseparable from the ensemble. It was a vision that would culminate in what we now call Maxwell's equations. The process of creating these equations was far from simple. Maxwell had to reconcile empirical observations, experimental results, and Faraday's visionary ideas with the rigor of mathematics. Faraday's lines of force, while deeply insightful, were intuitive sketches, beautiful metaphors without precise quantification. Maxwell saw them as more than metaphors. He recognized that if they could be expressed mathematically, they would reveal the hidden architecture of physical reality. He began by translating Faraday's observations into analytical language, developing mathematical expressions that could describe how electric and magnetic fields interact, vary, and propagate. Each step required careful thought, imagination, and a willingness to question long-held assumptions. He started by considering electric charges. Coulomb's law had described the force between stationary charges, yet this was only part of the picture. Maxwell asked what would happen if the charges were in motion, if currents flowed, if the surrounding space was not empty, but filled with invisible lines of influence. He examined how these charges create electric fields that stretch out into space, how those fields interact with other charges, and how they change when the system evolves. Similarly, he considered magnetic poles, currents, and their associated fields. He asked whether these forces were separate entities or manifestations of a deeper unity. Slowly, patterns began to emerge, patterns that suggested a profound symmetry between electricity and magnetism, between cause and effect, between change and response. One of the most revolutionary insights came when Maxwell considered the dynamic interaction of fields. Faraday had shown that a changing magnetic field produces an electric current. Maxwell's genius was to recognize the complementary relationship. A changing electric field should, by symmetry, generate a magnetic field. This addition, which he called the displacement current, was crucial. It completed the theoretical framework, linking electric and magnetic phenomena in a continuous self-sustaining cycle. With this insight, the equations could describe not just static situations but dynamic, propagating waves that would later be identified as electromagnetic radiation. Maxwell spent years refining these ideas, laboring over complex derivations, checking each step against experimental data, and ensuring that the resulting equations were consistent and complete. His notebooks reveal pages filled with intricate calculations, diagrams, and notes, reflecting a mind both rigorous and inspired. He constantly tested the implications of each formulation, asking how it would behave under different conditions, whether it could account for known observations, and whether it could predict new phenomena. In doing so, he demonstrated a unique combination of creativity and discipline, intuition and precision, imagination and empirical rigor. By 1865, Maxwell had assembled his framework into a coherent theory, published in his landmark paper, A Dynamical Theory of the Electromagnetic Field. In it, he presented the four equations that would bear his name, though at the time they were expressed in a more complex, component-based form. These equations succinctly describe the behavior of electric and magnetic fields, how they interact with charges and currents, and how they propagate through space. They encapsulated centuries of discovery, from Coulomb to Ampere to Faraday, unifying them into a single, elegant system. In essence, Maxwell had given mathematics the power to describe the invisible forces that shape our world. The importance of these equations cannot be overstated. Maxwell's equations provided a theoretical foundation for understanding light as an electromagnetic phenomenon. They demonstrated that electromagnetic waves travel at a fixed speed, corresponding precisely to the measured speed of light. In doing so, they bridged the gap between electricity, magnetism, and optics, revealing that light itself is simply a vibration of electric and magnetic fields moving through space. This was a profound leap, transforming light from a mysterious agent into a predictable, measurable, and explainable part of nature. For the first time, humans could understand the unity of forces that govern the physical world. Maxwell's work was not only scientifically transformative, but also conceptually revolutionary. By introducing the notion of fields, he changed the way physicists think about space itself. Space was no longer an empty stage where forces acted at a distance. It became a medium filled with dynamic, interacting fields, capable of storing and transmitting energy. This field-based view of the universe would later underpin the development of modern physics, including Einstein's theory of relativity and the quantum field theories that describe fundamental particles. Maxwell had shown that abstract mathematics could reveal deep truths about reality, far beyond what instruments of the time could detect. The elegance of Maxwell's equations lies in their simplicity and universality. Despite describing the full complexity of electromagnetism, they can be expressed in just four concise relationships. They describe how electric charges produce electric fields, how magnetic poles produce magnetic fields, how changing fields induce one another, and how these fields propagate as waves. Within these equations lies the blueprint of countless phenomena, from the light that illuminates a room to the radio waves that carry music across continents. Maxwell had distilled the essence of centuries of experiment and observation into a form both compact and profound, a true triumph of human intellect. Yet Maxwell's achievement was more than technical brilliance. It was a product of his unique way of thinking. He combined analytical rigor with imaginative visualization, treating mathematics not merely as computation, but as a tool to understand the invisible. He saw patterns and symmetries where others saw isolated facts, and he pursued these connections with patience, humility, and relentless curiosity. For Maxwell, understanding the universe was not just a professional pursuit, it was a form of reverence, a way to perceive the hidden order and beauty that underlie all things. His equations also foreshadowed technological revolutions that would unfold long after his death. By predicting the existence of electromagnetic waves, Maxwell laid the foundation for wireless communication, radio, television, and modern telecommunications. Engineers and scientists building technologies in the 20th and 21st centuries relied on principles first articulated in his four relationships, even if they did not fully appreciate the elegance of the underlying theory. Maxwell's work demonstrates how fundamental science can shape civilization, even in ways its creator could not have imagined. Beyond practical applications, Maxwell's equations exemplify a philosophical shift in understanding nature. They revealed that simplicity can underlie apparent complexity, that unseen forces can be both consistent and measurable, and that mathematics can uncover truths inaccessible to the senses. In this sense, Maxwell was not only a physicist but a visionary philosopher, exploring the nature of reality itself through the dual lenses of reason and intuition. His equations serve as a bridge between observation and imagination, showing that the universe, while vast and complex, is ultimately intelligible. The creation of Maxwell's equations also illustrates the cumulative nature of scientific progress. They were not the product of a single experiment or insight, but of decades of observations, reflections, and incremental discoveries. Maxwell synthesized the work of Faraday, Ampere, Coulomb, and many others, adding his own revolutionary insight, the displacement current, and the unified field perspective. This synthesis exemplifies how great science builds upon itself, combining imagination with empirical knowledge to achieve breakthroughs that redefine our understanding of the world. Maxwell's equations also introduced a new way of thinking about causality and interaction. By showing that changes in one field produce changes in another, they emphasized the dynamic and interconnected nature of physical reality. This perspective encouraged future physicists to consider the universe as an interconnected web of cause and effect, laying the groundwork for later developments in both classical and modern physics. The equations were not static statements, but a dynamic framework capable of describing motion, propagation, and transformation across space and time. As Maxwell refined his work, he also emphasized clarity and comprehensibility. While the mathematics was sophisticated, he sought to make the principles understandable through diagrams, analogies, and explanatory notes. He compared lines of electric force to streams of water and visualized magnetic fields as loops circulating around currents. This ability to communicate complex ideas clearly allowed other scientists to build upon his work, extending the reach and influence of his insights far beyond his immediate circle. Maxwell's equations became a foundation not only for research, but for education, inspiring generations of students and researchers to explore the unseen forces shaping the universe. Through this combination of imagination, rigor, and insight, Maxwell transformed the understanding of electromagnetism from a collection of empirical rules into a coherent, predictive, and unified theory. The significance of this achievement cannot be overstated. It illuminated the nature of light, revealed the unity of forces, transformed the concept of space, and provided a framework that would shape all subsequent physics. Maxwell's equations are a testament to the power of human thought, demonstrating how careful reasoning, guided by curiosity and creativity, can uncover truths about the universe that are both beautiful and enduring. Even as Maxwell's four equations took their final form on paper, their deeper implications began to unfold in ways that far exceeded what anyone in his time could have imagined. They revealed a universe alive with invisible rhythms, a cosmos in which energy and information could flow through empty space, carrying with it the light of stars, the spark of lightning, and eventually the signals that would one day connect distant continents. Each equation was more than a formula. It was a lens through which humanity could perceive the hidden order of reality, a map that revealed the interconnectedness of forces that had once appeared isolated and incomprehensible. Maxwell understood that he had not merely solved a scientific problem, but had uncovered a fundamental truth about the fabric of nature itself. The first of these relationships described how electric charges produce electric fields. This simple yet profound idea illuminated a universal principle, that matter, by its mere existence, influences the surrounding space, extending its presence invisibly into the void. It was a concept that transformed the understanding of cause and effect. Objects were no longer isolated, they radiated influence, setting the stage for interactions that could propagate through space and time. Maxwell recognized that these fields were dynamic entities, not static constructs. They could shift, bend, and ripple in response to changes in the distribution of charges, a revelation that would later enable the understanding of electromagnetic waves. The second equation articulated the behavior of magnetic fields. Just as electric charges produced electric fields, currents and moving charges generated magnetic effects. Maxwell saw the beauty of symmetry in this relationship. Electricity and magnetism were not separate forces, but complementary aspects of a single, unified field. The motion of charges created magnetic lines that circulated in perfect harmony, like dancers tracing invisible paths through space. This symmetry hinted at a deeper order, a balance that pervaded all natural phenomena. It was the first glimpse of a principle that would resonate throughout modern physics, that apparent complexity often arises from underlying simplicity and unity. The third equation, incorporating Faraday's law of induction, described how changing magnetic fields could induce electric currents. This was a revelation of motion and transformation. Energy could move, shift, and change forms, traveling across space even in the absence of matter. Maxwell's insight here was profound, for it suggested that the universe was not static but alive with dynamic processes, waves of energy moving continuously through the fabric of reality. It implied that interactions could propagate, not instantaneously, but at a measurable speed, a principle that would later become foundational for understanding light, radio waves, and the very nature of communication. The fourth equation, the introduction of the displacement current, was Maxwell's crowning insight. By recognizing that a changing electric field could generate a magnetic field, he completed the symmetry necessary for a self-consistent theory. This subtle but powerful idea allowed for the existence of self-propagating electromagnetic waves. With it, Maxwell mathematically predicted that light itself was one manifestation of these waves, traveling at a speed determined by the properties of electric and magnetic constants. It was a theoretical triumph of unparalleled magnitude. Light, the most familiar of natural phenomena, was revealed to be nothing more and nothing less than the undulation of invisible fields. The universe was singing, and Maxwell had deciphered the score. While Maxwell's contemporary colleagues struggled to appreciate the full depth of these insights, their consequences slowly began to resonate. Heinrich Hertz would later verify the existence of electromagnetic waves experimentally, confirming Maxwell's predictions and providing empirical validation for his equations. The discovery of radio waves, radar, and wireless communication owes its origins directly to Maxwell's theoretical work. Every transmission of energy across space, every beam of light, every signal carried invisibly through the air or along cables, can be traced back to the elegant framework he created. In this way, his equations are not just abstract mathematics, they are the very blueprint for technologies that define the modern world. Beyond practical applications, Maxwell's equations also reshaped the conceptual foundations of physics. By demonstrating that space itself is filled with dynamic fields, he challenged the Newtonian notion of empty space as a passive backdrop for forces to act upon. Space became active, a participant in the interactions of matter and energy. This field-based perspective would later become central to relativity and quantum field theory, influencing the way physicists conceive of everything from the behavior of subatomic particles to the curvature of space-time. Maxwell had opened a door to a universe far more interconnected and dynamic than previously imagined. The creation of Maxwell's equations also exemplifies the profound synergy of intuition and logic. Maxwell was not merely a mathematician, nor merely an experimentalist. He was a visionary who combined imaginative thinking with rigorous analysis. He could visualize lines of force, waves of energy, and interactions in ways that transcended the limitations of instruments, while simultaneously ensuring that every visualization adhered to mathematical truth. This balance between creativity and precision allowed him to develop a theory that was both deeply elegant and empirically verifiable, a rare and powerful combination that defines the greatest scientific achievements. Maxwell's work also embodies a lesson about the cumulative nature of discovery. His equations did not emerge in isolation. They were built upon the labor of centuries of scientists, Coulomb, Ampere, Faraday, and others, each contributing pieces of the puzzle. Maxwell synthesized these contributions, added his own revolutionary insights, and created a unified theory that illuminated phenomena far beyond what any individual experiment could reveal. It is a testament to how human knowledge progresses, incrementally, collaboratively, and through the persistent efforts of those willing to see beyond the immediately observable. Despite the abstract and technical nature of his work, Maxwell never lost sight of the human and philosophical dimensions of his discovery. He often reflected on the beauty and harmony inherent in nature, recognizing that the elegance of his equations mirrored the elegance of the universe itself. For Maxwell, scientific understanding was not just practical, it was aesthetic. He believed that the pursuit of knowledge was intertwined with the pursuit of beauty and truth, and that the patterns revealed by mathematics were evidence of a coherent and intelligible cosmos. His equations were as much a form of art as of science, a bridge between human imagination and the underlying order of reality. Maxwell's equations also transformed the way physics was taught and understood. They became the foundation of electromagnetism as a formal discipline, guiding generations of students and researchers in exploring the properties of fields, waves, and energy. The conceptual shift from isolated forces to interconnected fields allowed scientists to tackle questions that had previously seemed insurmountable. From designing electrical circuits to understanding the propagation of light, Maxwell's work provided a comprehensive framework that unified theory and practice. The equations became both a roadmap and a compass, pointing the way toward new discoveries and technologies. Even as Maxwell completed his equations, he remained humble and reflective. He did not seek fame or accolades. He pursued understanding for its own sake, guided by curiosity, patience, and a deep appreciation for the beauty of the natural world. His notebooks reveal a mind constantly exploring, questioning, and refining, always seeking more elegant and comprehensive expressions of truth. This combination of humility and brilliance allowed him to work without the distraction of ego, focusing instead on uncovering principles that would stand the test of time. The impact of Maxwell's equations extends far beyond classical electromagnetism. They laid the groundwork for the special theory of relativity, which Albert Einstein described as fundamentally indebted to Maxwell's insights. They influenced the development of quantum mechanics, where fields and waves are central to understanding the behavior of matter and energy at the smallest scales. In essence, Maxwell's framework provided the scaffolding upon which much of modern physics would be built. Every wave, every photon, every electromagnetic interaction in the universe can ultimately be traced back to the principles he articulated. Maxwell's achievement also illustrates the power of human imagination to transcend the limitations of sensory perception. Electromagnetic fields, waves, and interactions are invisible. They cannot be seen directly with the eyes. Yet through careful reasoning, mathematical insight, and imaginative visualization, Maxwell revealed their existence, behavior, and properties. He demonstrated that reality is not limited to what is immediately observable, and that the universe holds truths accessible only to those willing to think beyond the surface. In doing so, he expanded the boundaries of human knowledge and perception. The enduring significance of Maxwell's equations lies not only in their scientific content, but in the methodology they embody. They exemplify how rigorous theory, grounded in empirical observation, can reveal profound truths about nature. They demonstrate the importance of synthesis, showing that seemingly disparate phenomena can be unified under a coherent framework. They highlight the role of imagination and visualization in scientific discovery, and the necessity of patience, persistence, and humility in the pursuit of understanding. In every sense, Maxwell's work represents a pinnacle of intellectual achievement. Maxwell's equations also transformed the way humanity interacts with the physical world. From the development of radio and television to modern telecommunications, radar, and wireless technologies, the practical applications of his theory are ubiquitous. They underpin the devices that connect people across continents, illuminate cities, and transmit information instantaneously. In this sense, Maxwell's work is both timeless and deeply practical. It connects the abstract realm of mathematics with the tangible realities of human life. Even in the philosophical and artistic realms, Maxwell's equations resonate. They reveal a universe of symmetry, elegance, and coherence. They suggest that nature is governed by principles that are comprehensible, predictable, and beautiful. They inspire wonder, showing that beneath the complexity of the observable world lies a deeper, orderly structure. For scientists, artists, and thinkers alike, Maxwell's equations are not merely tools. They are windows into the hidden architecture of reality, inviting us to explore, understand, and marvel at the cosmos. Through the creation of his equations, Maxwell achieved a synthesis of knowledge that few have ever matched. He combined the empirical insights of his predecessors with his own imaginative vision, producing a framework that explained, unified, and predicted phenomena across the entire spectrum of electromagnetism. His work demonstrates that science is not merely a collection of facts, but a coherent narrative, a story of connections, relationships, and underlying principles that reveal the hidden structure of the universe. The importance of Maxwell's equations is not limited to their immediate discoveries. They transformed scientific thought, influencing the way physicists conceptualize forces, fields, and interactions. They shaped the development of technologies that define modern life. They inspired subsequent generations of scientists to think beyond the visible, to question assumptions, and to pursue the hidden patterns that govern reality. Maxwell's equations are thus both a foundation and a beacon, a foundation for knowledge, and a beacon guiding future exploration. Maxwell's achievements remind us that great discoveries often arise from patience, curiosity, and the courage to see connections where others see separation. He combined observation with imagination, mathematics with philosophy, precision with vision. He revealed the unity of forces that had long seemed mysterious and disparate, providing a framework that would illuminate countless phenomena and guide the development of modern science. In doing so, he left a legacy that endures not only in the equations themselves, but in the spirit of inquiry and insight that they embody. Ultimately, the creation of Maxwell's equations represents the triumph of human intellect and imagination over the limits of perception. They are a testament to the power of vision, to the ability of one mind to see patterns invisible to the senses, and to articulate them in a form that transforms understanding. Through these four relationships, Maxwell connected electricity, magnetism, and light. He unified observation and theory. He bridged the seen and the unseen. In every sense, his equations are a work of genius, revealing the elegant structure of the universe and providing a foundation for the science, technology, and understanding that define the modern world. In the quiet study of the early 20th century, a young Albert Einstein pored over textbooks and papers that would shape the course of his life. Among them lay the works of James Clerk Maxwell, a mind whose insights had transformed the understanding of light, electricity, and magnetism. Maxwell's equations were not merely formulas to be memorized. They were windows into a universe governed by elegant, invisible laws. For Einstein, these equations were both a guide and a challenge. They revealed a startling truth. The speed of light was constant, unaffected by motion, a concept that defied the common assumptions of classical mechanics. This realization became the seed of a revolution, planting within Einstein the ideas that would ultimately reshape physics forever. Maxwell had shown that light was an electromagnetic wave, propagating at a fixed speed through space. Classical Newtonian mechanics suggested that velocities should simply add or subtract, but Maxwell's equations implied something different. No matter how fast an observer moved relative to the source of light, the speed of light remained unchanged. For Einstein, this inconsistency was not a flaw in Maxwell's work, but a profound clue about the nature of reality itself. It suggested that space and time were not absolute, as previously believed, but flexible, intertwined dimensions, capable of stretching and contracting in response to motion. The implications were revolutionary. Maxwell's precise and consistent framework had exposed a fundamental tension in classical physics, one that demanded a radical rethinking of the universe. The influence of Maxwell on Einstein went beyond specific mathematical relationships. Maxwell had demonstrated the power of unification, showing that seemingly separate phenomena, electricity, magnetism, and light, were in fact aspects of a single underlying reality. Einstein adopted this perspective, seeking unifying principles that could reconcile the contradictions between Newtonian mechanics and electromagnetism. In doing so, he was inspired to conceive the special theory of relativity, a framework that maintained Maxwell's laws while fundamentally altering the understanding of space, time, and motion. Maxwell's work had created the conditions for a revolutionary leap, offering both the conceptual tools and the philosophical vision necessary to imagine a new physics. Maxwell's equations also exemplified a crucial methodological principle, the use of elegant mathematics to describe physical reality. For Einstein, the beauty and simplicity of Maxwell's formulation were as compelling as the empirical accuracy. The equations revealed patterns and symmetries in nature that guided the mind toward truth even in the absence of direct observation. Einstein recognized that such mathematical structures were not arbitrary. They were reflections of the deep order of the universe. This insight influenced his own approach to theoretical physics, where intuition, guided by mathematics, became the pathway to discovery. It encouraged him to pursue ideas that could not be immediately tested experimentally, but could be validated through logical consistency and predictive power. The legacy of Maxwell's work was also evident in the conceptual leap from the tangible to the abstract. By describing fields that permeate space, Maxwell introduced the idea that the universe is not only a collection of particles, but also a network of interactions that can propagate without a material medium. This field concept became central to Einstein's thinking, particularly in his development of general relativity, where the gravitational field replaces the notion of force acting at a distance. Maxwell had expanded the scientific imagination, showing that reality could include entities and structures invisible to the eye, yet essential to understanding the physical world. Einstein's theories were a natural continuation of this vision, extending the field concept to encompass space-time itself. Maxwell's influence also instilled in Einstein a deep respect for consistency and logical completeness. The universality of Maxwell's equations, their ability to describe a vast array of phenomena with a compact and precise framework, served as a model for the kind of theory Einstein sought. He realized that any new physics must honor these principles, preserving the insights of Maxwell while extending them to reconcile apparent contradictions. This requirement of internal consistency became a guiding principle in the development of special relativity, ensuring that the laws of physics remained invariant across all inertial frames, and that the speed of light remained constant in every reference frame. Moreover, Maxwell's work exemplified the power of thought experiments and theoretical reasoning, a method Einstein would famously employ throughout his career. Maxwell had imagined invisible lines of force and propagating fields, translating abstract concepts into predictive mathematical forms. Einstein took inspiration from this approach, conducting mental experiments that questioned the nature of simultaneity, motion, and the passage of time. In this way, Maxwell's influence extended beyond content to methodology, demonstrating that the combination of imagination and logic could unlock truths far beyond immediate observation. The cumulative effect of Maxwell's influence was profound. By providing a complete and unified description of electromagnetism, Maxwell had revealed both the power and the limitations of classical physics. His equations exposed a tension that classical mechanics could not resolve, and in doing so, laid the groundwork for Einstein's revolutionary theories. The constancy of the speed of light, the interdependence of electric and magnetic fields, and the field-based conception of space were all essential elements in the conceptual shift that produced modern physics. Maxwell had shown that the universe is governed by precise and universal principles, and Einstein carried that insight forward, extending it to space, time, and gravity. Even the technological developments that followed underscored the continuity between Maxwell and Einstein. Radio, television, and wireless communication relied on electromagnetic waves, predicted by Maxwell decades before they could be demonstrated. The understanding of these waves provided both a practical and philosophical bridge to the relativistic worldview that Einstein formulated. Without Maxwell's foundational work, the theoretical structure of special relativity and the later development of quantum electrodynamics would have lacked a crucial basis. The intellectual lineage from Maxwell to Einstein demonstrates the power of building upon deep insights, connecting generations of thought in a coherent and transformative scientific narrative. Maxwell's influence also shaped Einstein's view of the unity and simplicity of natural laws. Maxwell had shown that disparate phenomena could be understood through a small set of elegant principles. Einstein adopted this guiding ideal, seeking theories that revealed simplicity underlying complexity. The idea that the universe could be understood through unified, mathematically precise laws became a cornerstone of modern physics, driving the search for general relativity, quantum theory, and ultimately, the ongoing quest for a unified theory of everything. Maxwell had provided a paradigm, a vision in which mathematics, logic, and physical insight converged to reveal the underlying structure of reality. In reflecting on Maxwell's impact, it becomes clear that his work did more than describe electromagnetism. It inspired a conceptual revolution. By revealing the deep connections between electricity, magnetism, and light, Maxwell prepared the ground for Einstein to rethink the nature of space and time itself. His equations demonstrated the power of unification, the predictive power of mathematical beauty, and the importance of imagination guided by rigorous reasoning. They served as both a foundation and a catalyst, enabling Einstein to question assumptions, explore new principles, and ultimately transform physics from classical mechanics to a modern relativistic understanding of the cosmos. The relationship between Maxwell and Einstein is a testament to the enduring influence of great ideas. Maxwell's insights were the sparks that ignited Einstein's imagination, showing him that the universe could be understood in terms of deep, consistent principles. Einstein's theories, in turn, expanded the framework Maxwell had created, extending its implications to space, time, and energy in ways Maxwell could only have imagined. Together, their work represents a continuum of intellectual achievement, bridging the 19th and 20th centuries and shaping the foundation of modern science. Maxwell's influence on Einstein exemplifies the profound interplay between theory and imagination. By providing a unified description of electromagnetism, Maxwell created both the challenge and the opportunity for Einstein to develop relativity. The constancy of the speed of light, the field-based conception of space, and the unity of natural forces, all revealed in Maxwell's work, became essential cornerstones for the revolutionary ideas that would reshape the understanding of reality. Maxwell had opened the door, and Einstein walked through it, forever changing how humanity perceives space, time, and energy. Through this intellectual lineage, it is possible to trace the birth of modern physics. Maxwell laid the groundwork with elegant equations and visionary concepts, demonstrating that the universe could be described through unified predictive laws. Einstein extended this vision, reconciling these laws with the relativistic nature of space-time, and in doing so, ushered in a new era of scientific understanding. The story of Maxwell and Einstein is one of continuity, inspiration, and transformation, a story of how one genius can illuminate the path for another, and how profound insight can reverberate across generations, forever altering the human understanding of the cosmos. The impact of James Clerk Maxwell's discoveries extends far beyond the confines of 19th-century laboratories, resonating throughout the modern scientific world and continuing to shape our understanding of the universe. His insights into electricity, magnetism, and light were not merely a culmination of prior knowledge. They were a transformation, a gateway to a new era in physics. Maxwell's work created a conceptual framework that allowed future scientists to explore phenomena previously thought inaccessible. It established the principle that the invisible forces of nature could be quantified, analyzed, and predicted, providing humanity with a tool to interpret the universe with unprecedented clarity and precision. Maxwell's equations, elegant and concise, encapsulate the interplay of electric and magnetic fields in a form that is both mathematically rigorous and profoundly insightful. Through these equations, he revealed that light is an electromagnetic wave traveling through space at a fixed speed. This discovery unified previously distinct phenomena, bridging the realms of optics and electromagnetism. By demonstrating that light, electricity, and magnetism were interconnected, Maxwell transformed not only the content of physics, but also its very approach. Scientists could now view the natural world as a network of fields and interactions, rather than a collection of isolated forces. This perspective laid the foundation for the development of quantum theory, relativity, and countless technological innovations. The legacy of Maxwell's work is evident in the technologies that define modern life. Radio, television, radar, and wireless communications all rely on the principles he articulated over a century ago. Every time a signal travels invisibly across the air, every instance of light being transmitted through optical fibers, every electromagnetic interaction that powers modern electronics is a testament to Maxwell's vision. His theoretical insights became practical tools, demonstrating that abstract mathematical reasoning can lead to tangible advances that transform society. Without Maxwell's unification of electricity and magnetism, much of today's technology, from smartphones to satellites, would be inconceivable. Beyond technology, Maxwell's work reshaped the philosophical and conceptual foundations of science. By introducing the field as a fundamental entity, he changed the way physicists think about space, energy, and causality. Forces were no longer instantaneous actions at a distance. They propagated through space with defined velocities, carrying energy and information. This shift challenged classical Newtonian assumptions and paved the way for the theories of relativity and quantum electrodynamics. Maxwell demonstrated that rigorous mathematical formulations could describe realities that transcend direct observation, showing that the universe is intelligible not only through experimentation but also through the disciplined application of reason and imagination. Maxwell's influence also extends into the realm of scientific methodology. His combination of experimental observation, theoretical reasoning, and imaginative visualization established a model for modern physics. By synthesizing the work of Faraday, Coulomb, and Ampere, and by adding his own revolutionary insights, Maxwell exemplified how scientific progress often arises from the integration of empirical data with bold conceptual thinking. His approach encouraged future physicists to seek unity in diversity, to search for underlying principles that connect seemingly unrelated phenomena. This methodological legacy has inspired generations of researchers to pursue theories that are both elegant and predictive, combining creativity with rigor. In education, Maxwell's work continues to serve as a cornerstone. Students around the world learn about the interdependence of electric and magnetic fields, the nature of electromagnetic waves, and the unity of light with the broader spectrum of physical forces. These concepts form the basis for understanding modern physics, electrical engineering, and communications technology. Maxwell's ability to convey profound truths through concise equations has made his work an enduring teaching tool, illustrating how deep insights can be communicated with clarity and precision. His legacy is thus both theoretical and practical, influencing how knowledge is transmitted as well as how it is discovered. The philosophical implications of Maxwell's discoveries are equally profound. By demonstrating the unity of natural forces, he revealed an underlying order in the cosmos. The universe, once thought to be a collection of discrete, unrelated phenomena, became intelligible as a coherent system governed by consistent principles. This perspective influenced not only physics, but also the broader worldview of scientists and thinkers, encouraging a search for harmony, symmetry, and unity in all aspects of nature. Maxwell's vision suggested that complexity arises from simple, elegant rules, an idea that resonates across disciplines from cosmology to biology. Maxwell's contributions also illustrate the enduring power of imagination in science. He visualized lines of force, waves, and interactions that were invisible to the eye, translating these concepts into mathematical expressions that could predict and explain observable phenomena. This ability to bridge the unseen with the quantifiable continues to inspire theoretical physics, where concepts such as quantum fields, virtual particles, and space-time curvature are understood through imaginative reasoning grounded in mathematics. Maxwell's work reminds us that human insight, when guided by logical rigor, can reveal the hidden architecture of the universe. The influence of Maxwell's work on subsequent scientific revolutions cannot be overstated. Albert Einstein himself acknowledged the centrality of Maxwell's equations in shaping the special theory of relativity. The constancy of the speed of light, the unification of electric and magnetic fields, and the conceptualization of space as a dynamic medium all provided essential elements for Einstein's groundbreaking insights. In turn, Maxwell's principles continue to underpin the development of quantum electrodynamics, particle physics, and modern cosmology, demonstrating the long reach of his ideas. His equations serve as a bridge between classical and modern physics, connecting centuries of thought in a continuous intellectual lineage. Maxwell's legacy also underscores the human dimension of scientific achievement. His work exemplifies the virtues of curiosity, perseverance, and intellectual humility. He pursued understanding not for fame or personal gain, but from a genuine desire to uncover the truths of the natural world. His meticulous attention to detail, combined with visionary insight, allowed him to perceive patterns that others could not, and to articulate them in a way that transformed human knowledge. This human story of dedication, imagination, and discipline continues to inspire scientists, students, and thinkers across generations. In reflecting on the lasting legacy of Maxwell's work, it becomes clear that his influence transcends the confines of any single discovery. He unified forces, revealed the nature of light, and introduced the concept of fields, providing a framework that continues to inform science, technology, and philosophy. His contributions demonstrate that fundamental understanding can have both practical and transformative effects, shaping the way humanity perceives and interacts with the universe. Maxwell's work is a testament to the enduring power of insight, imagination, and rigorous reasoning. Ultimately, Maxwell's legacy is a living one. Every technological advancement, every scientific breakthrough, every exploration of the cosmos in the modern era is, in some way, built upon the foundation he laid. His equations are more than formulas. They are a language describing the invisible structure of reality. They remind us that the universe, while vast and complex, is comprehensible, and that human curiosity, when combined with imagination and discipline, can illuminate truths that endure across generations. Maxwell's work continues to resonate, a timeless testament to the power of intellect and vision. Through his synthesis of electricity, magnetism, and light, Maxwell transformed both science and the way humans understand the natural world. His contributions laid the groundwork for modern physics, shaped technology, inspired philosophical reflection, and provided a model of scientific thought that balances imagination with rigor. The principles he uncovered continue to guide inquiry, enabling discoveries that extend from the subatomic to the cosmic scale. Maxwell's lasting legacy is a celebration of human understanding, a bridge connecting curiosity to comprehension, and a beacon illuminating the path for future generations of scientists. The impact of James Clerk Maxwell's discoveries stretches far beyond the abstract beauty of equations and theoretical constructs. His insights into electromagnetism laid the foundation for an entire technological revolution, creating the blueprint for innovations that would transform human civilization. By revealing the unifying principles of electricity, magnetism, and light, Maxwell provided a framework that enabled scientists and engineers to manipulate the invisible forces of nature, turning theoretical understanding into practical applications that touch every aspect of modern life. The pathways from his equations to the devices that define the contemporary world are both direct and profound, demonstrating the transformative power of fundamental science. At the core of Maxwell's contribution is the understanding that electric and magnetic fields interact in a predictable, quantifiable manner, producing electromagnetic waves capable of propagating through space. This insight was revolutionary, revealing that energy could travel across empty space without the need for a physical medium. The implications for communication were staggering. Prior to Maxwell, the transmission of signals over long distances relied on wires or physical carriers. Maxwell's theory suggested that energy could be sent invisibly, transmitted as waves, potentially reaching across continents. Though it would take decades for technology to catch up, the foundation was laid. When Heinrich Hertz later confirmed the existence of electromagnetic waves, the stage was set for the invention of radio, television, and wireless communication, all direct applications of Maxwell's principles. The development of radio and telecommunications illustrates the tangible consequences of Maxwell's work. Engineers applied his equations to design antennas, transmitters, and receivers, converting abstract theory into practical tools. By understanding how electromagnetic waves propagate, they could manipulate frequency, amplitude, and direction, creating channels for transmitting information invisibly and instantaneously. Every radio broadcast, every cell phone conversation, every Wi-Fi signal is a modern echo of Maxwell's insight that fields are not confined to matter, but can move freely through space. Without his theoretical groundwork, the concept of wireless communication would have remained a dream rather than a reality. Maxwell's influence extends beyond communication into the realm of energy and electronics. Electrical generation, transmission, and distribution are all governed by principles he elucidated. Power grids rely on alternating currents, magnetic induction, and controlled electromagnetic interactions, all concepts that Maxwell formalized mathematically. Engineers designing transformers, electric motors, and generators exploit these relationships to convert mechanical energy into electrical energy, and vice versa, enabling the widespread use of electricity that defines modern life. From lighting homes to powering industry, from medical equipment to transportation, the practical applications of Maxwell's work are both pervasive and indispensable. In optics and imaging technologies, Maxwell's insights also had a profound effect. By demonstrating that light is an electromagnetic wave, he provided the conceptual framework for understanding the behavior of lenses, prisms, lasers, and optical fibers. Telecommunications, medical imaging, and scientific instruments all rely on controlling and manipulating light waves in precise ways. Fiber optic networks, which carry vast amounts of data across the globe, operate on principles that can be traced directly to Maxwell's equations. The ability to transmit information as light pulses, without interference from physical barriers, is a testament to the enduring applicability of his theoretical work. Maxwell's contributions also laid the foundation for radar and remote sensing technologies. By understanding how electromagnetic waves reflect, refract, and interact with materials, engineers developed tools to detect objects at great distances, map terrain, and even explore space. Radar systems that monitor weather, guide aircraft, and ensure national security rely on his fundamental principles. Similarly, satellite communication and GPS navigation are built upon the predictable behavior of electromagnetic waves, demonstrating that Maxwell's vision of propagating fields underpins technologies that modern society often takes for granted. The principles Maxwell uncovered also play a crucial role in medical technologies. MRI machines, for example, exploit electromagnetic fields to image internal structures of the human body with incredible precision. Electromagnetic waves are manipulated to interact with atomic nuclei, producing signals that can be converted into detailed images. This application illustrates the profound versatility of Maxwell's work, showing that the same equations describing light and radio waves also govern interactions at the atomic level. From diagnosis to treatment, from imaging to therapy, modern medicine relies heavily on the technological legacy of Maxwell's discoveries. Even in computing and information technology, the influence of Maxwell is undeniable. High-speed data transmission, wireless networking, and electronic circuitry all depend on controlling electromagnetic phenomena with precision. Engineers design circuits and devices using principles derived from his equations, ensuring signals propagate accurately without loss or interference. Microchips, sensors, and antennas all operate under the framework he established, highlighting how theoretical insights into invisible fields have tangible consequences in the digital age. Without Maxwell, the interconnected, data-driven world we inhabit today would be impossible. Maxwell's work also inspired a broader technological vision, influencing generations of inventors and engineers to explore applications beyond the immediate scope of his discoveries. Nikola Tesla, Guglielmo Marconi, and countless other pioneers drew upon Maxwell's equations to develop devices that revolutionized communication, power distribution, and automation. Even innovations that Maxwell could not have envisioned, such as Wi-Fi networks and satellite internet, are possible because the fundamental behaviors of electromagnetic waves were fully articulated by his theories. In this way, his legacy extends far beyond the laboratory, shaping the trajectory of technological progress across more than a century. Furthermore, Maxwell's influence is not confined to earthbound technologies. Space exploration, astronomy, and astrophysics rely on understanding electromagnetic phenomena to observe and analyze the universe. Telescopes detect light across the electromagnetic spectrum, from radio waves to gamma rays, interpreting signals that have traveled millions of light years. Spacecraft communicate with Earth using radio signals governed by Maxwell's principles. Satellites orbiting the planet rely on electromagnetic interactions to maintain communication and navigation. Maxwell's equations, though conceived in the 19th century, have enabled humanity to reach beyond the confines of our planet and explore the cosmos. The transformative impact of Maxwell's work illustrates the profound synergy between theoretical insight and practical innovation. By uncovering the underlying laws of electromagnetism, he created a bridge from abstract mathematics to real-world applications that touch every aspect of human life. His legacy is evident in the electrical grids that power cities, the communication networks that connect continents, the medical devices that save lives, and the technologies that allow us to explore the universe. Maxwell demonstrated that fundamental science, when pursued with vision and rigor, has the power to shape civilization itself. Maxwell's equations continue to guide research and innovation, providing a framework for emerging technologies such as wireless energy transfer, photonics, quantum computing, and advanced communication systems. Modern scientists and engineers still rely on his insights to design, predict, and optimize systems that manipulate electromagnetic fields with incredible precision. The universality and robustness of his principles ensure that they remain relevant, enabling continued technological progress in ways Maxwell could never have imagined. Ultimately, Maxwell's work exemplifies the enduring connection between theory and practice. By articulating the laws governing electricity, magnetism, and light, he transformed the invisible forces of nature into tools that humanity could understand, manipulate, and harness. The technologies that define modern civilization, from telecommunications to computing, from medical imaging to space exploration, are built upon the foundation he established. Maxwell's vision of a unified, mathematically precise, and predictable universe continues to illuminate the path of innovation, demonstrating that profound theoretical insight can catalyze extraordinary practical achievement. Through his pioneering understanding of electromagnetism, Maxwell did not merely describe the natural world, he empowered humanity to shape it. His legacy in modern technology is both foundational and transformative, reminding us that the pursuit of knowledge, guided by imagination and rigor, can yield innovations that change lives, societies, and the world itself. From the first equations he wrote to the countless devices and systems operating today, Maxwell's influence is omnipresent, a testament to the power of scientific insight to transcend generations and revolutionize the way humans interact with their environment. James Clerk Maxwell, though celebrated in scientific circles, remains less known to the wider world compared to figures like Einstein or Newton, yet his influence on modern physics is nothing short of monumental. Maxwell's discoveries provided the intellectual scaffolding upon which the entire edifice of 20th century physics was built. By unifying electricity, magnetism, and light into a single coherent framework, he created the conditions that allowed Albert Einstein to question the assumptions of classical mechanics and ultimately formulate the theory of relativity. Maxwell's genius was not only in the creation of equations, but in the conceptual leap he achieved, a leap that revealed the hidden structure of reality and transformed the way humans perceive the universe. Before Maxwell, electricity and magnetism were treated as separate phenomena. Scientists like Faraday and Ampere had made tremendous empirical discoveries, but these remained largely descriptive, without a unifying mathematical theory. Maxwell's insight was to recognize that these forces were intimately connected, bound by precise laws that could be expressed in elegant equations. By demonstrating that changing electric fields produce magnetic fields and vice versa, he revealed the existence of electromagnetic waves that travel through space at a constant speed. This was more than a scientific breakthrough. It was a paradigm shift. It showed that the universe is governed by principles that are consistent, predictable, and universal, and that light itself is a manifestation of these invisible underlying forces. Maxwell's work, though published in the mid-19th century, laid the foundation for Einstein's revolutionary thinking decades later. The constancy of the speed of light, an intrinsic property revealed by Maxwell's equations, was incompatible with the Newtonian understanding of absolute space and time. Einstein recognized that if Maxwell's laws were universally valid, the classical notions of simultaneity and relative motion had to be reconsidered. This insight became the seed of the special theory of relativity. Without Maxwell's equations, the profound inconsistencies that drove Einstein to rethink the very fabric of space and time would have remained hidden. In this sense, Maxwell is not merely a predecessor, he is a direct enabler of modern physics. Despite the revolutionary nature of his contributions, Maxwell did not achieve the same level of fame during his lifetime. His work was highly mathematical and abstract, often difficult for contemporaries to fully grasp, and the implications for future technologies were not immediately apparent. While his theories transformed the understanding of light and electromagnetism, much of the public and even the scientific community focused on experimental verification and practical applications, such as Hertz's demonstration of electromagnetic waves, rather than appreciating the visionary breadth of Maxwell's conceptual framework. As a result, his name became overshadowed by those who later applied or popularized his insights. Yet the reach of Maxwell's genius is evident in the trajectory of scientific discovery. Every subsequent development in electromagnetism, from radio to quantum electrodynamics, owes its existence to the principles he articulated. Technologies that define the modern world, wireless communication, radar, MRI imaging, fiber optic networks, and satellite systems, are all manifestations of the structures Maxwell revealed. Beyond technology, his conceptual vision provided the intellectual backdrop for the most transformative theories in physics, influencing Einstein, Lorentz, and the pioneers of quantum theory. Maxwell's equations are not merely tools, they are a lens through which the universe can be understood, a language in which the cosmos itself seems to speak. Maxwell's brilliance lay not only in unification but in foresight. He imagined phenomena that could not yet be directly observed and provided a mathematical framework to describe them. The idea that electromagnetic waves propagate through space independently of matter was revolutionary, anticipating technologies and discoveries decades into the future. This combination of theoretical insight and predictive power is a hallmark of scientific genius, and it is precisely this quality that enabled Einstein to see beyond the apparent limits of Newtonian mechanics. Maxwell's vision revealed the invisible scaffolding of reality, allowing Einstein and others to build upon it and explore concepts of space, time, and energy that were previously unimaginable. The designation of Maxwell as a forgotten genius is a reflection not of the significance of his work, but of its subtlety and abstraction. Unlike inventors whose creations have immediate and tangible effects, Maxwell's contributions were conceptual and mathematical, requiring a level of abstraction and imagination that few contemporaries could fully appreciate. The physical reality of his predictions, radio waves, electromagnetic radiation, and the unification of light and electromagnetism, was only gradually confirmed by subsequent experiments. Over time, his influence became more visible, but his name never achieved the popular recognition of Einstein or Newton. Nonetheless, for those who study the foundations of physics, Maxwell's genius is undeniable, for without his insights, the very structure of modern science would be fundamentally different. Maxwell's influence also underscores the interconnectedness of scientific progress. His work exemplifies how breakthroughs often depend on prior discoveries, and how one visionary mind can unlock possibilities for generations to come. By unifying disparate phenomena, Maxwell provided a template for thinking about the universe in terms of fundamental principles and symmetry. Einstein, standing on Maxwell's shoulders, was able to take the next step, exploring the relativity of space and time, while future scientists extended these ideas into quantum mechanics and beyond. Maxwell's legacy is thus both foundational and catalytic, a quiet force propelling the evolution of human understanding. Moreover, Maxwell's approach highlights the enduring importance of theoretical science. He demonstrated that understanding the fundamental principles governing nature can yield insights far more profound than any single experiment. By applying mathematics to conceptualize the invisible forces of the universe, he unlocked a framework that not only explained known phenomena, but predicted unknown ones. His vision shows that the pursuit of knowledge for its own sake can have consequences that extend far beyond immediate observation, influencing both technology and the philosophy of science for centuries. The story of Maxwell also serves as a reminder that genius is not always recognized in its own time. The subtlety and abstraction of his work required future generations to fully appreciate its depth. Einstein's acknowledgement of Maxwell's influence is perhaps the clearest testimony. Without Maxwell, the conceptual leaps that led to relativity and the modern understanding of light and energy might not have occurred. Maxwell's legacy is thus both humbling and inspiring, a demonstration that the most profound contributions may remain underappreciated until their consequences unfold across time. Ultimately, James Clerk Maxwell deserves recognition as one of the greatest minds in the history of science. His equations transformed the understanding of electromagnetism, unified disparate phenomena, and revealed the true nature of light. By providing the conceptual foundation for Einstein's theories and for modern technological innovation, Maxwell's work has reshaped both science and society. Though his name may not be as widely known, his influence permeates every corner of the modern world, from the devices that connect people to the theoretical frameworks that describe the universe itself. He is, in every sense, the forgotten genius who made Einstein possible, a visionary whose insights continue to illuminate the path of discovery and understanding.